Okay, let's say we have two parallel plates, metallic, and they're separated by some distance d, and they each one have a surface area of A. We put some positive charge in one of them, and then we put equal amount of negative charge in the second one. There is insulator between them, so the charge is not going to cancel out. But as a result of this charge distribution, we will have an electric field between the two plates. It starts from the positive one and it ends to the negative one, which is almost uniform. If the length of this parallel plates are very large comparing to D, then you don't have to worry about the edge effect. But in the edge, it would be a little distorted field. Okay? We can ignore that for the sake of simplicity and just think about a uniform electric field between the two parallel plates. Now the question is, how much is this electric field? I want to know how much is that. I want to use the Gauss law. Now the trick is very simple. I'm going to use a Gaussian cylinder. In this Gaussian surface, we know that the electric field outside is 0 because this negative and positives are facing each other and it's metal. Then these charges are going to move around and redistribute themselves in a way that they are as close as possible to each other, and thus in the outside there will be no charge. So electric field outside this, sometimes referred to as a capacitor, is technically 0. So this is capacitor. Inside the metal, also the electric field is 0, so I don't have to worry about it. The only electric field I have is the electric field which is parallel, perpendicular to the plate, and it only passes through this little tiny surface. Call it A1. No electric field line passes through the side surface, and no electric field passes through the A3 surface here on the top. So the flux passing through this Gauss surface would be only the flux which passes through surface A1, and it would be E times A1. But how much charge do we have stored on this part? Now, suppose I put initially some amount of Q charge, positive charge, on top of this positive plate. The charge which is enclosed in this surface is related to the total amount of charge put on the entire surface. So I can define sigma, which is the surface density, surface or charge surface density, equal to the total amount of charge divided by the total amount of area, which is the same as if I say the charge enclosed divided by the surface area A1 here. So the flux would be also Q enclosed divided by epsilon 0, where I can replace this charged enclosed by sigma times A1, and then flux would be divided by epsilon 0. Now, these two equations are the same. So if you put them equal, you will see E dot A1, then it would be equal to sigma A1 divided by epsilon 0, which you can conclude that the electric field would be sigma divided by epsilon 0. Constant. Sigma is constant, epsilon 0, the permittivity of the vacuum is constant, and so electric field would be uniform. Now notice that I only use the positive plate, not the negative plate. I didn't use both of them at the same time. I used only one of them. Now, you could have repeat this one for the negative plate, and you would get exactly the same electric field uniform above the negative plate. But you don't have to use both of them. You don't have to mix them. You can only use one of the plate, and you would get the electric field between the two plates correctly.